friends, how are you? I hope you all are well. Today's topic is electrostatic potential and capacitance. This is one of the important topics in your second year. So, in this video, I am going to explain what is electric potential. Before explaining electric potential, we have to know what is electric potential energy. That's why I have mentioned here electric potential energy and electric potential. First we will see what is electric potential energy. Electric potential energy. See here, suppose this is a source charge. Here one test charge is there. I want to bring this test charge from a point of infinity to a point. For example, I want to bring to this point, point P. This charge I want to bring here. Definitely, I have to do some work. The work what I shall do, that work will be stored at this point in the form of potential energy. I am giving one simple example, it will be clear. Why I am taking this charge from a point of infinity to this point? Listen carefully. Suppose this is fixed. One spring is there. Here I have taken one block. Think that it's a wooden block. Now this is in the equilibrium position. Here in this case the force applied is 0. At the same time the potential energy stored here is also equal to 0. Now what I am doing, this side is the fixed. I am compressing the spring. So the block is like this. The spring is already compressed. That means I have done some work. Now if I leave this, definitely the block will move. The block will move. When the block will move, that means the block will get the velocity. If the block gets the velocity, I can say that the block gets the kinetic energy. From where this kinetic energy came? This kinetic energy came when I compressed it. Or you can say that I applied the force on this wooden block this side. I applied the force. It compressed. So in that compressed position, compressed state, the work what I did, it stored in the form of potential energy. So when I released it, that potential energy only converted into kinetic energy. I would like to say that the work what I did, compressing the spring by applying force, you can say external force, that work only stored in this place in the form of potential energy. You can say that the mechanical potential energy, which is also equal to electric potential energy, what I am going to prove it. Let us see. So what is electric potential energy? Now listen carefully. In this case, the force is applied 0, but here the force is applied F. Okay. So in this case force is applied 0. Now if I take a, suppose this is a charge, source charge. So if this is a source charge, so definitely surrounding that one electric field will be there. Now if I move away to away, definitely the strength of the field will decrease. So we assume that the force of this charge at the point infinity is equal to 0. How I said that in this case force applied 0, we can imagine that, we can assume that the force due to this charge is also 0. Where it is 0? It is 0 at infinity. That means nobody has seen the infinity. Here, whenever we move away to away, the force decreases. Ultimately, one stage comes where we can assume that its impact is not there or force is equal to 0. So, the thing is that I want to take the charge from a point of infinity, is that at the point of infinity, the effect of force due to this source charge is equal to 0. How I started from force equal to 0 to force equal to Fa. Similarly, I want to bring this charge from infinity where the force is equal to 0. Suppose I bring this charge from here to here, the point P, here to here. Definitely, I did some work, or you can say work done by external force. Work done by the external force. You know that if this is a positive charge, this is a positive charge, so there will be repulsion. So I have to do the work against it. That means work done is positive. Work done is positive. Suppose you think that this is the negative charge, or you think that this source charge is negative, this test charge is positive. Okay? All the time we take the test charge as positive. So in this case what will happen? No need to apply any external force, because this is the negative charge. Ultimately it will pull here. It will pull towards it. Whenever it will pull towards it, from where that energy came, that energy is spent by it, which is stored in the form of the potential energy. In that case, the work done by the system, whenever this is negative, this is positive, this negative charge is pulling it due to this attractive force. In that case, the work done by the system, we say that work done by the system is negative. If the work done by the external force is positive, that means here work done by the system is negative, because the system is utilizing its potential energy. Here the kinetic energy is due to the conversion of a potential energy stored by the charge. So I would like to say what is electric potential energy. Thereafter I shall derive what is electric potential. Okay? Now let us see. Electric potential energy. We write generally by the symbol U. So, the potential energy means electric potential energy of a charge at a point is defined as the work done in bringing that charge, work done in bringing that charge from the point of infinity. I have written work done in bringing that charge to a point from the point of infinity. This is the source charge. This is the test charge. It is at infinity. I want to bring that charge to this point, for example, this point P. So this charge is Q I am bringing here. Okay? Suppose this distance is R. So whenever I am telling the potential energy of the charge at a point, don't think that potential energy stored in this point. In practically, potential energy stored in this system. The point may be here, 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 the point may be here. Thou I have written potential energy of a charge at a point, but in practically the potential energy present in that system. Okay? So the potential energy of a charge at a point is defined as the work done in bringing that charge, bringing that Q charge, suppose, to a point from the point of infinity, is called the electric potential energy. Mathematically, I can write that this W is equal to 1 upon 4 pi epsilon naught Q into Q divided by R. Listen carefully. This capital Q is the source charge. This small q is the test charge. Okay. So work done is equal to 1 upon 4 pi epsilon naught, or you can say that is the K Q into Q, the two charges, source charge and test charge. Okay. I brought to the distance, that is small r. Now you see that this is Q, this is Q, both are positive, so there will be a repulsion. I want to bring to this point P. Okay, this distance I said that is equal to R. Now you listen carefully. So here, suppose this charge is not plus Q, this is 2 coulomb. Then what I shall write? So I can write 1 upon 4 pi epsilon naught Q into Q. Sorry, in place of Q, I shall use the 2 coulomb divided by the distance. Okay, why? Since Q is equal to 2 coulomb. For example, if Q is equal to 10 coulomb, then what I shall write? I shall write in place of small q 10 coulomb divided by R. Clear? In this case, you see that all whatever the charge here, I am multiplying. In place of small q, I am writing. Okay. Now you observe that this one is fixed. This one is fixed. Then only the small q, what is the test charge I have taken, that is only changing. Now see here. This is the work done, or what I can say, this is the electric potential energy. So in this case, this electric potential energy, or U is equal to W, this is equal to 1 upon 4 pi epsilon naught Q into Q divided by R. Listen carefully. In this case, this is the potential energy. If I use the unitary method, the work done for bringing a single unit positive charge. Listen carefully. This is 1 upon 4 pi epsilon naught Q by R. Why? Here Q is equal to plus 1 coulomb. I have taken that is plus 1 coulomb. So this is the electric potential. Here in place of small q, what I have written? I have written only 1 coulomb. That means 1 upon 4 pi epsilon naught q by r. Listen carefully. So, in this case, in place of a charge q, I have taken 1. That means the amount of work done for bringing a single unit of positive charge. Listen carefully. This is work done per unit charge. Work done per unit charge. Listen carefully. I wrote that W is equal to 1 upon 4 pi epsilon naught q by r. If I divided by q, then how much left? 1 upon 4 pi epsilon naught q by r. This is the work done per unit charge, or you can say that this is the potential, electric potential. Okay, this is electric potential. This is the amount of work done for bringing a single unit positive charge from a point of infinity to this point. Single unit, one charge, or written here 1 coulomb. That means I can say that the electric potential is the potential energy per charge. So I can write the definition of electric potential is electric potential. What is this? The amount of work done. Amount of work done for, or you can say in bringing, the amount of work done in bringing a single unit of positive charge, test charge we say, from a point of infinity to a point. The amount of work done in bringing a single unit of positive charge from a point of infinity to a point is called the electric potential of that point, or I can say that this electric potential is equal to potential energy per charge. Then what is the SI unit? SI unit of potential energy is equal to joule. Then what is about the potential? Potential is equal to joule per coulomb, or that is, you can write joule per coulomb, or that is only volt. This is the differences between electric potential energy and electric potential. Okay, so potential energy is the work done for bringing that charge from a point of infinity to a point, but here potential is the work done for bringing a single unit charge, single unit positive charge from that point to this point to a point is called the electric potential of that point. Let us see that. See here, this charge is plus charge, here also plus charge. I want to bring it from here to here. The potential energy definitely will be the positive. Suppose this is the plus, this is minus, this charge is minus, this is the plus. Then in this case what will happen? The potential energy will become minus, because here the system will do the work. Here work done by the external force or work done by me, particular work done by the system. If this is plus, suppose this is minus, same thing will be minus. Now suppose the Q is minus, okay, this is also, you think that this is also minus, then what will happen? The work done or the potential will be positive because there will be repulsion. So I have to do the work done by the external agent, that is the positive, and work done by the system, that is a negative. So this is the basic differences between electric potential and potential energy. You see this way. Now suppose this is the positive charge, okay. Now this is the infinity, here the plus Q charge is there. I brought that charge to this point P, okay. Same thing in different way. Suppose this distance is R. Whenever I am bringing it, I am bringing it very slowly. However, its kinetic energy is 0. That much slow I am bringing. For example, I brought it to this point. Now, here to here, the distance is x. Now, suppose I moved it from here to here, very small distance. This small distance is dx. I change its position very slowly from this point to this point. Suppose I moved it a very small distance which is equal to dx. Okay? Now listen carefully. In this case, the force will be equal to 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught Q into Q divided by R square. Listen carefully. This is the force, or you can say electrostatic force. So according to the Coulomb's law, I have written 1 upon 4 pi epsilon naught small capital Q into small q divided by R square. Now we'll see that work done. In this case, we know that work done is equal to force into displacement. Work done is the force into displacement. Okay. Now in this case, force is equal to 1 upon 4 pi epsilon naught Q into Q. Suppose I brought, now the object is here. Suppose object at this point. So in this point, the distance how much? The distance is x. I have taken here to here, the distance is x. So I have written x square. This is force into displacement. Suppose I moved it from this point A to B. So the small distance, that is equal to dx. I am bringing this side, that's why I am writing this is minus dx. Listen carefully. So the work done, very small work done, that is equal to 1 upon 4 pi epsilon naught q into q by x square, because here to here the distance is x I have taken. So x square, here to here I am coming back this side, that's why I have taken this is minus dx. So if I want to take find the complete work, so I can say that this work is equal to negative 1 upon 4 pi epsilon naught q into q 1 upon x square into dx. So this is from infinity to the distance r. I am bringing it from the point infinity to this distance. to this distance, I have written the integration from infinity to r. So in this case, I can say that this is equal to minus 1 upon 4 pi epsilon naught q into q. This is constant 1 by x square x to the power minus 2. Okay. So otherwise we will write like this. No need to worry. So I can write here 1 of x to the power minus 2. So 1 upon x. Okay. 1 upon x. This is from infinity to r. So I can say that this is, so I have taken the minus here, I have written, so that's why minus became here minus 1 by x, minus it became plus. So I can say that this is, whether it is appearing or not, I am writing here. So this work is equal to 1 upon 4 pi epsilon naught q divided by r. 1 by r minus 1 by infinity, that is 0, 1 by r. This is equal to potential energy. Just what I said. This potential energy is equal to 1 upon 4 pi epsilon naught q into q divided by r. This is the potential energy. And so far the potential is equal to 1 upon 4 pi epsilon naught q upon r. This is the potential, because in place of charge I have taken 1. So children, this video is about electric potential energy and electric potential. I hope that you might have understood it clearly. So until the next video, bye.